4.2 Antiderivatives as Areas. Part 2 Definite Integrals. Southwestern College, Professor Maria Olivas. Section 2 Definite Integrals. To recap, we can use rectangles to estimate the area under a curve. Let's draw some pictures to represent this. I'm going to draw two coordinate planes. The first one focuses more on quadrant 1, whereas the second one is focusing in on quadrant 1 and 4. In the first coordinate plane, I'm going to draw a continuous random curve. This represents a function. It's going to be between the interval from A to B. I'm going to draw line segments going down from the starting point and the ending point on the function going down to the x-axis. I'm going to label those as x equal to A and x equal to B. I'm going to draw a rectangle, a left endpoint rectangle within the curve going down towards the x-axis, and I'm going to shade that in. So this is going to represent one of those rectangles that we were using when we were finding our Riemann sums. In the second coordinate plane, I'm also going to draw a random curve that starts in quadrant 1 and goes down below the x-axis to quadrant 4. I'm going to draw from the endpoints line segments going towards the x-axis. For the first one, I'm going to label that as x equal to A, and the second one, I'm going to label that as x equal to B. I'm going to draw a rectangle, a left endpoint rectangle in quadrant 1 above the x-axis, and I'm also going to draw a left endpoint rectangle in quadrant 4 below the x-axis. So these rectangles that I have drawn in, I'm now going to shade those in. Now I'm going to draw a curve connecting the area from our rectangle in quadrant 1 to a capital letter A, which is going to represent area. So our capital letter A is going to be equal to f of x times delta x, and that represents the area inside of that rectangle. I'm going to show that this is equal to a positive quantity because it's above the x-axis. So I know it's technically not equal to this, what I'm going to show right now, but it's something that I want to show that it represents. So I want to show that it's equal to a positive quantity. So I put a plus or a positive and I circled it. For the bottom rectangle, or the one in quadrant 4, I'm also going to draw a curve with an arrow pointing towards the capital letter A, which is going to be equal to f of x times delta x. Now, because this area is beneath the x-axis, I want to show that this is equal to a negative quantity. So I'm going to show that this is equal to a negative sign, and I'm going to put a circle around it, and it's just to represent that it's equal to a negative amount. And I've also labeled the y-axis with f of x. So comparing these two pictures, we can now see that in the problems we've done beforehand, we've only had to worry about finding the area of rectangles that were above the x-axis. So they were always going to give us a positive amount or a positive quantity. Now, going forward, we're also going to have to keep in mind that we are also going to be working with problems that we might have to add positive and negative values together to come up with what we're going to call a net area, right? Because when we have a function that is above the x-axis, that's going to give us a positive amount. But if we have a function that is below the x-axis, then that's going to give us a negative amount. And when we add those together, we can think of that as a net area. Okay, let's go on to the Riemann sum estimate. So the Riemann sum estimate is going to be the summation from I equal to 1 up to n of f of x sub I times delta x. And this is what we were using to come up with an estimate or an approximation. As we can see from the second picture, the Riemann sum will actually give us what we call net area. And I've put a cloud around that net area. Exact value of the net area is going to be represented with the limit as n goes to infinity of the summation from I equal to 1 up to n of f of x sub I times delta x. and that will always give us the exact value of the net area. Definition of definite integral, and I've drawn a little cloud around definite integral. This is going to be the integral from a to b of f of x dx, and this is going to be equal to our net area. And it's equal to the limit that we had written up above it, where it says exact value of the net area. Note, f must be continuous for the function to be integrable. Example 4. Evaluate the integral from -2 to 1 of x plus 3 dx. So that x plus 3 represents our f of x. It represents our function. I know that x plus 3 or f of x equal to x plus 3 is a continuous function, so we can definitely integrate that. Our limits, our upper bound and our lower bound, I've highlighted them here. The lower bound I've highlighted in green, which is -2, and the upper bound I highlighted in blue, which is 1. And I've also highlighted in green the a and in blue the b from our definition of definite integral. So I've written below example 4, f of x is equal to x plus 3. And then I've written the closed interval from -2 to 1. So we are now going to evaluate our function at our limits of integration. So f of -2 is going to be equal to -2 plus 3, which is equal to 1. And f of 1 is equal to 1 plus 3, which equals 4. So now that we have those values, we actually have a pretty good idea of what the picture for this is going to look like. So I can draw a picture representing this. I'm going to draw a coordinate plane here that is focusing in on quadrant 1 and 2. I'm going to label some values here for the x-axis. I'm going to label from -2 to 1 with a scale of 1. For the f of -2, the ordered pair that represents that is going to be -2, 1, and for f of 1, our ordered pair is going to be 1, 4. Let's begin by drawing a point at -2, 1, and now I'm going to also draw a point for 1, 4, and connect those 2 points with a line segment. I've also drawn little tick marks on the y-axis with a scale of 1 up to the value of 4. I've drawn vertical lines going down from my ordered pairs that I just plotted, and here it looks like I have created a shape. If I look at the enclosed region here from where below the function all the way down to the x-axis, and then in between that closed interval from -2 to 1. So I'm going to shade in the region here that I'm looking for the area of. I'm going to shade it in, I'm going to highlight it in yellow so that it stands out. Now looking at this shape, you should have an idea of what this shape is. So first let me begin by asking, what shape is this? So hopefully you all said this is a trapezoid. Yes, this is a trapezoid. So if we know how to find the area of a trapezoid, we could find the area to this region. So the area for a trapezoid is going to be a is equal to 1/2 times h, which represents the height, times the quantity, little b plus big B. So let me label my b's here. I'm going to label little b as the line segment connecting -2, 0 and -2, 1, and big B is going to be the line segment connecting 1, 0 and 1, 4. The measurement for little b is going to be equal to 1, and the measurement for big B is going to be equal to 4. And you could get that by subtracting the y values. I'm going to go ahead and draw a line segment underneath the x-axis between -2 and 1. And that measurement is going to represent 3 units. And once again, you could get this one because we're going horizontally this time. You could subtract the x values here for those ordered pairs. So if I took the x values, I could take the larger x value, which would be 1, and then subtract -2 from it. So that would be 1, or b minus a, for my interval there, 1 minus a -2 is equal to 1 plus 2, which is equal to 3. So that's going to represent the 3 units for that distance. That's going to be representing our h, our height of our trapezoid. Let's go ahead and plug everything into the formula. A is going to be equal to 1/2 times h, which is 3, times the quantity 1 plus 4. So A is going to be equal to 1/2 times 3 times 5. And this is all multiplication now, so we can go ahead and just multiply in any order since multiplication is commutative. So it's going to be 1/2 times 3 times 5, so that'll give me 15 halves. And that's going to represent the area for our region. So the integral from -2 to 1 of x plus 3 dx is going to be equal to 15 halves. I'm going to go ahead and box that in. And we are done with that problem for example 4. Let's go on to example 5. Evaluate the integral from -1 to 4 of 2x minus 4 dx. So we're going to use the same technique here for this one. The function in this case is going to be the 2x minus 4, so I'm going to represent that as f of x equals 2x minus 4. And then I'm going to evaluate this function at the limits of integration. So here the limits of integration is going to be from -1 to 4. And I've highlighted those. I highlighted the -1 in green, I highlighted the 4 in blue, and I highlighted the function, the 2x minus 4 part, in yellow. So we're using that closed interval from from -1 to 4. F of -1 is going to be equal to 2 times -1 minus 4, which is equal to -2 minus 4, which equals -6. F of 4 is equal to 2 times 4 minus 4, which equals 8 minus 4, which is equal to 4. Now we are ready to start drawing our graph. So looking at this, I can tell that the ordered pairs I will be using -1, -6 and 4, 4. So let's go ahead and draw our coordinate plane. So we can go ahead and plot these points and start drawing our function. Here's my coordinate plane. And now I'm going to go ahead and plot my points. Let's go ahead and draw some tick marks here. First, I'm going to start drawing tick marks on the y-axis. I'm going to draw tick marks all the way down to -6 with the scale of 1. And I'm going to draw tick marks up to 4, +4 on the y-axis, also with a scale of 1. On the x-axis, I'm going to draw tick marks that range from -1 to +4 with a scale of 1. I'm going to start off by plotting the point -1, -6, and then I'm going to plot the point 4, 4, and connect them with a line segment. I'm going to draw an ordered pair at the y-intercept, which is at 0, -4. I'm going to also make the line segment a little more bolder here, and I'm going to make line segments one going up from -1, -6 to the x-axis, and one coming down from 4, 4 to the x-axis. And now I'm going to highlight the region of which I'm going to find the areas of. The triangular region that is above the x-axis, that area I'm going to highlight in yellow, and the triangular region that is below the x-axis I will highlight in green. I'll call the triangular area above the x-axis A sub 1, and the triangular area below the x-axis, I'll call that one A sub 2. All right, in order for me to have more space here, in order to find these areas, I'm going to take all of the work that I did beforehand. I'm going to lasso all that in, and I'm going to just make it smaller and move it slightly upward in order to create more space for me. And I'm going to draw in here a line segment underneath a sub 1 to represent the base, and a line segment next to a sub 1 representing the height. And I'm going to draw a little arrow pointing at a sub 1, and I'm going to write down the word triangle. Actually, let's make that triangled, and I'll draw 2 arrows to each one of this a sub 1 and a sub 2 regions. So I need to find the area of these triangles. I'm going to draw a line segment separating the work that I did beforehand and the work I'm going to do now. So the work below this line segment is going to represent how I find the area of these triangles. I'm going to write down area of a triangle is equal to A equals 1/2 times base times height. We need to find the area of a sub 1. So I'm going to write a sub 1 equals 1/2 times the base, but we don't know the base. In order to find the base, I need to find the x-intercept of where this function crosses the x-axis. So I need the x value for the x-intercept. Let's find that x-intercept. In order to find it, I need to substitute f of x equals 0. So I'm going to write f of x equals 2x minus 4. 0 equals 2x minus 4. Add 4 to both sides of the equation to solve for x. I have 4 equals 2x, divide by 2 to both sides, and I am left with 2 is equal to x. So my x-intercept here is at 2, 0. I need to change my little tick marks that I had drawn earlier, because in order to make sure that that x-intercept is represented right at 2, I need to make sure I redraw these. All right, so now that I fixed that and I reshaded my a sub 1 here because it disappeared, I can now go back and substitute that value for the base. If I take away 2 from 4, I end up with 2. So that length for that base is 2. I need the height. The height is going to just be 4 because I can tell by looking at that one of the first points I plotted at 4, 4, that y value was at 4. So for a sub 1, that's going to be equal to 1/2 times 2 times 4, which is equal to 8 halves, which reduces to 4. So that value for that triangular region, that area for a sub 1, is going to be a positive 4. And I'm going to circle that 4, and I'm going to draw an arrow at it saying that it's a positive, because anytime we find an area that is above the x-axis, we are going to represent that value with a positive value. Positive because area is above the x-axis. A sub 2 is going to be equal to 1/2 times, we need the base. And once again, to find that base, I'm going to go back to my triangle here on the coordinate plane. I need to find that distance from -1 to 2. So I'm going to go 2 minus -1, which is 2 plus 1, which is equal to 3. So my base is going to be equal to 3. My height is just going to be that y value of that first ordered pair I plotted. So that was at -6. Actually, it's going to be the absolute value of that because it's a distance. So it's just going to be a 6. So 1/2 times 3 times 6 is equal to 18 halves, which reduces to 9. I circled that in red, and I'm drawing an arrow at it, and I'm saying this value has to be negative. It's negative because the area is below the x-axis. So we talked about this. Remember that when we talked about definite integrals, we said that the integral represents a net area. So that's why sometimes the value might end up being a negative. Even though we're finding areas, that value might still be negative. I'm going to take all my work that I showed here in the coordinate plane and where I found the x-intercept. I'm going to lasso that in and make it slightly smaller and move it upward so that I have more space. So now that I move that upward, I've got a little bit more space here below that spot, and I can write some more things here. I'm going to write in the integral from -1 to 4 of the quantity to x minus 4 dx is going to be equal to 4 minus 9, which is equal to a -5. And that's going to be the definite integral, what it's equal to. It's equal to a -5. We're going to box in that answer. So again, the integral does not represent total area. The integral represents net area, which is why this value is a negative value. Let's go on to example 6. Use geometry to find the value of each integral. Draw a picture. So this is going to be our 6a problem. This is going to be the integral from 0 to 5 of 2 dx. If we think of the function f of x equals 2, and I just highlighted in yellow that 2, which represents f of x, you should be thinking of a horizontal line. So f of x equals 2 is the same thing as y equals 2. And I'm going to write down it's a horizontal line. Since the limits of integration are from 0 to 5, we're going to be working within the closed interval from 0 to 5. I'm going to draw a coordinate plane, so a y-axis and an x-axis, focusing in on quadrant 1. I'm going to draw tick marks on the x-axis, and it's going to be from 0 to 5 with a scale of 1. And I'm going to draw tick marks on the y-axis from 0 to 2 with a scale of 1. And I'm going to draw a horizontal line at y equal to 2, or f of x equal to 2. Now, what I want to do is I want to work within that region from 0 to 5. So I'm going to draw vertical line segments going down from my function to the x-axis at x equal to 0 and x equal to 5. And I will shade the area of the region that is enclosed, and I'll highlight that in yellow. So this is what I'm looking for. I'm looking for the area of this yellow shaded region, the region that is bounded between the function f of x equals 2, the x-axis, and x equal to 0 and x equal to 5. That's the area I'm looking for. So I'm going to draw a arrow pointing at this figure, and this is a rectangle. And I'm going to draw another arrow from the word rectangle, and that means I need to find the area of a rectangle, which is equal to length times width. So I need to know the length, and I need to know the width of this rectangle. So the width of this rectangle is going to be 2, and the length is going to be 5. So 2 times 5 is going to be equal to 10. So the integral from 0 to 5 of 2 dx is equal to 10 square units. We're just going to write 10. And we're going to go ahead and box that answer in. And we have found the area of that rectangle. So yay! Let's move on to 6b. 6b says the integral from 1 to 3 of the quantity x minus 4 dx. So this time I'm looking at this, and the function here, in this case, it represents f of x equals x minus 4. And I know that that is a linear function. So I'm going to draw a line to represent that. So first, let me highlight what represents my function here. I'm going to highlight in yellow the x minus 4, and I'm going to rewrite that as f of x equals x minus 4. So this is in slope-intercept form. I can tell that my slope is 1, and my y-intercept is going to be at 0, negative 4. I'm going to write my slope also as 1 over 1 so that I know what my rise and my run is. Makes it easier. And we're working within the closed interval from 1 to 3. So now that I have all this good information here, I need to find f of 1 and f of 3. F of 1 is equal to 1 minus 4, which is equal to negative 3. And f of 3 is equal to 3 minus 4, which is equal to negative 1. So that's going to give me those ordered pairs that I need to help me draw that line segment that I'm going to be connecting here in my coordinate plane. That's going to represent the part of my function that's represented within that closed interval from 1 to 3. So for f of 1, we're going to have the ordered pair 1, negative 3, and for f of 3, we're going to have the ordered pair 3, negative 1. Let's go ahead and draw our coordinate plane. So I'm going to go ahead and draw my coordinate plane, focusing in more on quadrant 4. I am going to draw tick marks on the x-axis from 0 to 3 with a scale of 1. And then I'm going to draw tick marks on the y-axis from 0 to negative 3 with a scale of 1. I'm going to plot the ordered pair 1, -3, and I'm going to plot the ordered pair 3, -1. I'm going to connect those 2 points with a line and extend my line. I am going to go ahead and cross out the page number, which is a 5 here at the bottom of the page, and I'm going to write in 0, -4, just so that there is no confusion. And then I'm going to go and I'm going to draw vertical line segments at x equal to 1 and at x equal to 3 to enclose the region of which I am trying to find the area of. And I'm going to shade that region in green so that you can clearly see where I'm trying to find the area. I'm trying to find the area of the region bounded by the function, the x-axis, x equal to 1 and x equal to 3. I'm going to draw a line segment on the x-axis here showing the length of the height of this trapezoid, which is 2. And I'm also going to find the 2 bases. The larger base is going to be 3 and the smaller base is going to be 1. Since this is a trapezoid, I'm going to write in trapezoid and I'm going to write down the formula for the area of a trapezoid, which is area is equal to 1/2 times h times the quantity little b plus big B. Area is going to be equal to 1/2 times h. The height in this case is 2. I'm going to write that as 2 over 1. And times the quantity 1 plus 3. Here the 2's will cross cancel and I'll be left with a equals 4 because 1 plus 3 is 4. So it's going to be 4 units, but remember that this is an area and this area is below the x-axis. So therefore, since the area is below the x-axis, we need to represent this value with a negative number when we're talking about the definite integral that we just found. So the integral from 1 to 3 of x minus 4 dx is going to be equal to -4. Let's go ahead and box in that -4. That's going to be our final answer for this one. Going on to example number 7. Suppose the marginal profit function for a company is given by the derivative of p of x is equal to -2x plus 60. Let's highlight where it says marginal profit function and let's highlight p prime of x is equal to -2x plus 60. Where p prime of x is measured in dollars per unit, let's highlight that as well. And find the total profit from the production and sale for the first 30 units. Let's highlight total profit from the production and sale of the first 30 units. Let's highlight that in a different color because that's what we're being asked to find. So our profit is going to be represented with the integral from 0 to 30 of -2x plus 60 dx. So we need to evaluate our derivative of p of x. The derivative of p of x is equal to -2x plus 60. We need to evaluate this at our limits of integration. So the derivative of p of 0 is equal to -2 times 0 plus 60, which is just equal to 60. The derivative of p of 30 is equal to -2 times 30 plus 60. And if I do this and work it out, I'm going to just end up with a 0. So now that we have these values, we have the ordered pairs 0, 60 and 30, 0. I can go ahead and plot these on a coordinate plane and I can draw a picture. So let's go ahead and draw a coordinate plane here. On this coordinate plane, I'm going to label the point 30, 0. And I'm also going to label the point here 0, 60. I'm going to connect those 2 points with a line segment. So I can clearly see here the region that is bounded by the function, the x-axis, and it's in between x equal to 0 and x equal to 30. I'm going to just go ahead and lasso in the work that I did previously, and I'm going to make it slightly smaller, and I'm going to move it over to the left so I have more space to write in the units for the y-axis. First, let's begin by writing in the units for the x-axis. So the units for the x-axis are just going to be units because it did say that the derivative of p of x is measured in dollars per unit. I'm going to go ahead and draw a cloud around the words dollars per unit in the word problem, and I'm going to draw an arrow pointing towards the y-axis. I'm going to write a dollar sign over the word unit to represent dollars per unit for that one. I'm going to go ahead and shade in yellow the region that is bounded by the function, the x-axis, and x equal to 0 and x equal to 30. So I'm going to go ahead and highlight that in yellow so it stands out. And then I can see by shading in this region that this is a triangle. I can see that it's a right triangle because the corner where the y-axis and the x-axis meet, that's a 90-degree angle. So I'm going to go ahead and draw a square there. I'm also going to label a 60 for the height and a 30 for the base. The formula for the area of a triangle is A is equal to 1/2 times base times height. So for this triangle, it's going to be A is equal to 1/2 times, I'm going to write 30 over 1 times 60 over 1. When I multiply that out, A is going to be equal to 1,800 divided by 2, which simplifies to 900. So this now represents our total profit. The integral from 0 to 30 of negative 2x plus 60 dx is equal to $900. And I'm going to make sure I write that dollar symbol to represent the units, and I'm going to box in that answer because that is my final answer there. I'm just going to lasso in that work that I did right there at the very last line just to make it slightly smaller so it fits a little bit nicer. I'm going to highlight the BH from the formula of a triangle, highlight it in blue, and draw a little arrow pointing to the side over here. And I'm going to show the units, how I came up with the units. Since we're multiplying dollars per unit times units, the units will cross cancel and my answer will be left in just dollars. That's how I know that I need to write a dollar sign here to represent the units for my final answer.